So let's talk a bit about a purist's guide to type-driven design in Go. I am Angus Morrison. I am one of the purists you'll be getting very intimate with this evening. I was genuinely going to introduce myself as a Go expert, but I did just get that question wrong. So I'm Angus. I know some Go. That's what we got. I'm currently working at JP Morgan on a project so secret it has an actual unironic code name that I am not allowed to tell you. Okay? Just to build a bit of mystique about what I do. Type-driven design, if you're not familiar, is kind of distillable down to the idea of using a language's type system to make invalid data unrepresentable. So ideally, we want to statically assert, using the compiler, that any piece of data that is entering into our domain logic is legit. So if we have something that represents a user, we know that if an object of that user type exists, it must be correct. If you've got your London Gophers bingo cards with you, yes, congratulations, you can tick off the pass don't validate reference. If you don't know what this blog post actually is, but you may have heard the phrase pass don't validate since 2019, I really, really do recommend it. This introduces the idea of type-driven development using the concept of two types, a list type and a non-empty list type. So this is a non-empty list type that has a lot of extra sort of semantic meaning bound up in it. That means you have to immediately throw away all of your junk code that does if list is not empty, then. Why do we care about any of this? Why do we want to make writing types harder and more arduous for us than it seems to be already? Well, actually, if we can get the compiler to do a load of work checking errors for us, that reduces a huge class of things that can go wrong in production at runtime. We know that if data exists, it is valid. Bad inputs simply can't harm our system because they are not allowed to exist, and chucks away a load of developer mistakes that we're all very familiar with. Testing, as we will see demonstrated, is also easier and coverage is greater, and it will massively, assuming you don't do some very interesting things with the English language, which I know we're all capable of as developers, improve the readability of your code. So this sounds pretty great. But Go doesn't make this easy for us. If you've ever met a Rust enthusiast, of which I am one, if you know someone who works in Haskell, this is the issue with the pass don't validate blog posts. People tend to switch off a little bit because it gives all of its example in Haskell. You'll know that Haskell has the mother of all type systems. Rust as well, very strong, expressive type system. Go, not so much. If you speak to some more academic types, you say you work in Go, you might see a little turning up of the nose, a little feeling of superiority, because Go's type system is flimsy. Let's say, we don't have certain features, we have no ability to enforce immutability versus mutability. It's always mutable. We have no concept of algebraic data types, which is the ability to express this thing or that thing or the other. We only very recently got generics, which is nice because now everyone can shut up about how Go doesn't have generics. And of course, we can just choose that we're going to step outside the type system at any time by saying this thing is an empty interface type. Good luck. So there is some audience participation. Those of you who've chosen to sit at the back, well done. Good option. Those of you at the front, less so, because here is where I'm going to be looking for the hands. So given what we all know about Go and the Go type system, who believes that robust type-driven Go can, in fact, be implemented? A show of hands for A at compile time. This is the gold standard for type-driven development. Literally no. Oh, 1, 2. Yes, we know where the optimists are, and they're never sitting at the back. It's not how it works. B, runtime. We will need some help for the Go runtime, but we can do this seamlessly, ergonomically. It's going to feel really good. A few more, okay, but we're majority pessimist in here tonight. Good crowd. C, also runtime. It can be done. It's going to be monstrous. It's going to be absolutely appalling. Okay, we haven't given up all hope for Go just yet. And finally, D, this can't be done in Go. There will be a way around whatever checks we try and put in place. Okay, no one's completely lost the faith. I like it. Pass me my water. Thank you very much. I'd like you to all engage in a bit of a thought experiment for me. Hands up if you came here with someone, either from work or someone you know already. Cool. You lot are in a bit of a safer position. If you're sitting next to a stranger, just take a quick look at them. Just out the corner of your eye is fine. You don't have to make the full eye contact. You have no idea what that software engineer is capable of. Okay, and that is a very scary thought. Think of how bad the code, like from people you know, is. Then think about the people who you do not know. And so for the last 20 minutes, we're going to be talking about uncompromising and dogmatic type-driven design in a Byzantine application. And a Byzantine system is a system in which you have one or more actors that is actively hostile to the overall health of the system. So we're going to be working in a single example application, and we are going to assume that any code written by anyone who isn't us, we're going to control the business logic. We are going to assume that that code is hostile and is looking to smuggle bad data into our system, okay? Smuggling bad data into our system is what excites these developers, these end users, okay? So we must assume that all other software design philosophies are dangerous. They are out to get us. We need to assume that all other software engineers, I mean, we already know that we don't know what they are capable of. And also our past and future selves, because I don't know about you, but I look at code that I wrote 2 months ago and I don't know what I was thinking. Why are we doing this? What is the point in this thought experiment? Well, when we take an idea all the way to its extreme, we go right past the point where it is maximally useful and has a huge amount of value to us, to the point where it's nonsense. And that point where we identify that it is maximally useful before it becomes too much of a headache, that is where we get the most benefit. Commandment 1, because we're purists now, remember, we do things in a very formal way, no matter the consequences for our application. Thou shalt not validate. And yes, the AI generators will replace the artists. They will. I'm going to introduce you to our sample app for the evening. It exposes a very simple endpoint to create users. Okay, it's structured using hexagonal architecture. It's very close to the idea of ports and adapters. If you haven't used this before, don't worry about that. Basically, the key idea is that we have the nice, safe, pure domain logic we control. We have a very simple HTTP handler. We have a very simple store of data that we'll call a repository. And the horrible, nasty code that we don't control in both of these things depends on our business logic. So our business logic dictates the rules to anything that is external and gives us a nice, safe shell to work with. So our users package will contain our domain logic. We can see here, I'm so sorry, you guys at the back, this is a nightmare. Our service interface defines essentially the access for HTTP handlers into our code, and it creates a user. It's really very simple. You probably have code running like this right now. I definitely see this on the regular. And it just takes an email, a password, a biography as a string. It constructs a user and returns it. It specifies a repository as well, which is a simple interface to any old store of data. And if we look at how our user is implemented, there's nothing special about this. Email, a password hash, biography. And our bio, we're going to say, is optional. Could be an empty string. We don't care. Don't recommend doing this in production. If you allow a user to specify any kind of string they like, the probability of that ending up as just a base 64 representation of someone's genitals is 100%. Don't do it. We have a very simple HTTP handler here for creating users. This will look like a lot of code you've written before. It just passes the body and then funnels it on through into our service where our domain logic lives. And finally, the implementation of that service, you can see we validate this email, we validate the password, we hash the password, we invoke our repository to store that user, and assuming there's no error, we return the user and nil. Okay, pretty simple. Who's seen code like this before? Yeah, a lot of nodding. Most people, I think. Good. This is horrible. Please stop. I'm begging you. There's a few reasons for this. Active validation, as I call this, where we step through and validate each input one by one. It captures a point in time, okay? It makes no guarantees whatsoever of ongoing validity. And in that code, we were just trusting that the user that comes back from the repository is actually the user we expected to have, which as purists, we know is insanity, okay? You are going, at some point, to forget to validate those inputs. I do this quite regularly, and apparently I managed to forget to test those validations in my test suite as well. This will happen because we're human. It generates a ton of boilerplate, as we've just seen. The noise ratio compared to like the actual business logic, which is just passing something onto a repo, is massive. This is also a testing nightmare. Like when you're testing your domain logic, like really the only thing we care about here is repository call succeeds or repository call fails, right? Two cases. But the way we've written this, we now end up in a situation where we also have to test, well, what if email validation fails? What if password validation fails? What if password hash validation fails? Like this is now pretty much a self-contained integration test. Where do we go from here? Commandment 2 for the purists in the room. Thou shalt declare new types. New types. I'm about to introduce something I call naive type-driven design. Spoilers, this is not where we're going to end up. Our service.create endpoint, if I switch branch very rapidly here, now takes, instead of these raw strings, a pointer to a create user request. And this create user request is itself very, very simple, but it's composed of the email, the password hash, and the bio that we've seen before. But these are now all typed. Before they were raw strings. Now we have an email address type, a password hash type, and a bio type. And the definitions for these aren't particularly exciting. An email address is a wrapper around a raw string. The key thing here is that all of these types come with exported constructors. So new email address like asserts that an email address vaguely follows a format that we expect, and assuming that that is true, it will return an email address. If it doesn't, it returns an error. But rather than all of that error handling and testing being wrapped up in our domain logic, which we know is pure, is clean, is beautiful, we have our user handler, which is now responsible before it is ever able to pass us values that may be invalid. It has to first get valid values to pass us. Yeah, this is what's creating the safe shell around our domain. This is still problematic though, okay? In languages like Rust and C++, this kind of pattern of creating one type to very specifically represent the concept that you are dealing with and must be valid is known as a new type. Those languages have some built-in protections to help you implement these things. We have some issues, however. First and foremost is you see we're now returning, or we're now accepting in our create method, a pointer to our create user request. And as purists, we know that pointers are very dangerous. We've heard about what can go wrong with pointers. And what I'm worried about here is that if we accept a pointer type, the thing that that pointer points to, the referent, that can change out from underneath us at any time. Some psychopath fires off a Go routine before passing us that pointer, does something absolutely nefarious that changes that value. Remember, we can't trust the people sitting next to us. We don't know what we are going to end up with. And moreover, inside this create user request, this email address, this password hash, and even this raw string inside the email address, these are all exported fields, okay? Anyone, anywhere in the application can just come in here very conveniently. It's very convenient that Go lets us do this and change this value to whatever they like. Okay, so how can we improve in the first stage on this naive approach? Although we sacrifice the convenience, you should always require explicit getters and define explicit setters if they are necessary, and those setters must also define valid data transitions. They have to enforce that data integrity for the type. Pointer inputs and return values, as we know, they're dangerous, but also these structs, these request structs we're dealing with, and what most applications deal with, like they're pretty small. It's a bundle of strings, and a string is essentially just a pointer and a length. That's a cheap copy. Okay, go under the hood, might not even choose to escape a type like that to the heap. But there's something else here. There's something actually much more dangerous that as purists we should be fearing deeply, and it's very Go specific. Does anyone have any idea what that might be? Why will it undermine our new types and their strong validations? Okay. Commandment the third, thou shalt not permit zero values to enter. Zero values are a uniquely Go-ish problem. Zero values of our domain types, which are exported, they bypass our constructors completely. Anyone from anywhere in the program can choose that they are going to give us an empty, i.e. junk, create user request, and they can do this from anywhere, whenever they like. And moreover, our definition of zero here is actually quite complex, because it's not just that the whole object is empty, it's that any field inside a complex struct which should be non-zero renders the whole domain object invalid when it is zero, even if the others are valid. So start getting in the habit of thinking of these domain types as either complete or incomplete. Complete is valid, incomplete is not. And a question you might ask is, can we solve this by making our domain types unexported, but making their setters and getters exported? And the answer is yes, this does actually work, and it completely bulletproofs us against a lot of these problems. On the other hand, it hides absolutely all of those exported methods from documentation, your IDE tooltips, and although we may be purists, we're not completely unhinged. Please don't do this to the teams in your organization. Do not have, or at least don't make a habit of using exported methods on unexported types. That way lies misery. But what if we do something else? What if we validate that domain types are complete? Package reflect gives us a useful utility to detect zero values, but as we've already seen, that doesn't solve for completeness. So let's take a slightly different approach. Why don't we look at branch number 3 here? And here I've created a TypeDD package, which we consider safe because this is part of something that we control. We have declared this. And we've declared an interface complete, which is something that can be manually implemented to signal to the rest of our system. Unfortunately, we're getting into runtime territory at this point, that a type does indeed have all the fields that it's meant to have, and all of those fields are correct. So complete is very simple. It just returns true. Or false if it's not complete. And you can see that for our create user request, that's implemented in terms of, well, is the email complete and is the password hash complete? We don't care about the bio. It's optional. It can be complete or not. And when we drill down all the way to primitive types and we start looking at our IDs and strings, complete is simply asserts here that our email address is not an empty string. Why isn't it doing more complex validation than that? Well, actually, that's because the only 2 cases we now have to handle are the cases where someone is giving us a valid value that they have got from a constructor, so we can trust it. If it exists, we trust it. That is the beauty of type-driven design. Or they've given us a 0 value, in which case the string is empty. There is no state in which, once that object is completed, if it is not 0, we then have to validate exactly in what way this thing is wrong. It doesn't feel good to me. I hope it doesn't feel good to you, because we're kind of back in validation territory, which is what I promised you we were going to try to avoid. There's an interesting point at work here, though, because whereas validation errors can come in a great many varieties, like an email address can be wrong in many ways, a password can violate your policies in many ways, completeness errors are actually of a single kind, because users cannot cause completeness errors. If a constructor is correctly called, you will get a valid value, or the request simply will not proceed. Only developers, and I told you not to trust the people sitting next to you, only developers can cause completeness errors. Only they can accidentally pass you a 0 value into your domain. And that means that completeness errors are detectable at development time. What that means, and you might ask, why can't we, well, we can test for this. We have integration tests. This is what they're for. Integration tests are collaborative. They span concerns. We don't have complete control. And as purists, that unnerves us greatly. So we can borrow a technique from very deeply untrustworthy languages like C, languages like C++, where you can literally add a number to a pointer and get another number, and suddenly you access memory that is vastly outside the bounds of your own program. These guys have figured out how to protect themselves from some of this form of mischief, and that is the idea of using build tags to conditionally compile our non-zero assertions, because we know that these assertions can only happen at dev time, which means we can choose exactly when we're going to do this kind of validation. So now our service, you'll see this is an unexported constructor, but it's building our service in just the same way as it was before. Our service release, to show you that one first, has a build tag of release, and all this does is provide, it's essentially a decorator, an exported new service wrapper around our standard service type. Debug is a bit more interesting. When we use the debug build tag, we can actually wrap all of the assertions that check for these non-zero values in code that does not exist in production. It only exists at development time. So this structure, all it does is create our legit, it takes an instance of our legit service and it wraps it, it decorates it with some of these assertions that make sure the values coming in are complete. So we can catch out hostile developers trying to sneak these things into our system. And I feel pretty good about that. I think we're still in elegant territory. Yes, we've invoked the runtime. We need a bit of help, but none of this stuff exists in production. We're only having to validate one kind of thing outside of our constructors. So those of you who chose option B, all right, feel good. All right, feel yourselves up straight. You've done it. Enjoy the feeling. You haven't. We have a much bigger problem. First, let's make things a bit more difficult for ourselves. Optional values, values which must be valid if they are present, but they are allowed to be absent. We're not that restrictive, okay? Conditionally empty value, consider patch requests, okay, where you partially update an object. In the traditional Go approach, you would represent an optional value with a pointer type, okay? Nil signifies the absence of a value, so you're not going to update that. Non-nil pointers to a zero value signifies the removal of an existing value, and a non-nil pointer to a non-zero value signifies that you're going to replace it with a new value. But we know that pointers can't be trusted. Yeah, like Go likes to promote pointers as a nice, efficient way to do things, but this is about trust. This is about purity, okay? We want to be clean. So how do we handle the case of a non-nil pointer to an incomplete complete value? Okay, is this thing incomplete because it needs to be removed, like legitimately, or is it incomplete because someone has bypassed the constructors and given us an invalid zero value? Okay, we're going to talk about options, which is a pattern those of you familiar with languages like Rust may have seen before. And might believe that Go's type system isn't very well equipped to do this, but actually, in our case, it is. So we're now dealing with an update user request, which is, as you'd expect, very similar field to the create user request, but some of them are optional. Option, given a type of option T and two constructors, none and some, where T is of any type, we can describe all three of these possible cases. None requires return simply, this option is empty, do not update this, okay? And the beauty of how option none is designed is that its zero value is valid. Its zero value is none, none simply returns the zero value of option T. There's no way to smuggle an invalid option to us using its zero value. Some's a little more complicated, okay? Some indicates whether or not this creation is present and therefore should be updated. For anything that isn't a complete type, so for anything that is not necessarily complete, then like if the value exists, like we don't care about its validity, okay? That's fine. We're willing to update the type to, or the value to whatever is contained in this option. However, if it is meant to be complete, we have this interesting case where if it is 0, that is legit because that's telling us to change the update so that it is setting that field to empty. If it is non-zero, but it is not complete, that means it has ended up in a horrible in-between state where one of its fields, or one or more of its fields, may be 0, but others are present. That is invalid. And to detect that, we have to do something slightly nasty with reflection and our complete interface types, which getting into ugly territory again, but this is also something that you can hide behind build flags. You don't have to do this reflective checking in production, because again, completeness errors like this, they come from developers, not from users. Things are going to get ugly, okay? Now, shan't make thread-safe copies. We've talked about pointers, right? Trusting no one. We can't accept pointers because they change underneath us, okay? Hence, we can't accept slices. We cannot accept maps because these are implemented as pointers. The person who's given you that map has retained a copy, and being the dangerous individuals we know they are, they're going to change that unexpectedly in a Go routine. If only Go provided us some way where we could deterministically control the means of construction of a pointer type's data in a thread-safe way. I'm really sorry about this. No one should have to see Go used in this way. Imagine if we replace all slices in our constructors instead with variadic parameters. And a variadic parameter, if you're not familiar, it allows you to pass one or more of a certain type to an option, and Go will very nicely and conveniently collect that into a slice for us. And that slice is then under the control of our constructor. That's ours. The outside world can't get hold of that. And of course, as purists, like we congratulate the presence of a massive, expensive copy in our code base. If we take a look at this on branch number 5, all of these branches, by the way, are numbered and labeled after the concepts I'm talking about, if you do want to follow again later. In our models, we have the concept now of a bulk update user requests, which is just a slice of update user requests. Okay? If there are none of these, this is invalid. But we're more interested in this concept of a safe bulk update user request, where we take a variadic number of update requests, and that slice that is created, that's ours. Okay? We've copied, but it's ours, and we feel safe and we can sleep at night. What the hell do we do about maps? Okay, how do we turn a map into a set of variadic parameters? Okay, well, it's really very simple. Nothing could be more simple, nothing could be more elegant, nothing could be more pure. What we are going to do is take our map and define a new type, a pair, which has a key, a t, which is comparable to act as a map key, u of any, which is just any kind of value, and a constructor, of course, because we like nice strong constructors, which will build these pair types. And then all the caller into our domain has to do is decompose their map into a slice of these pairs. They simply spread those pairs into our domain constructor, where Go very, very conveniently for us copies them into a slice. And then we iterate over that slice and in fact reconstruct the map. 3 copies, ladies and gentlemen, 3 copies. This will be completely lost on the people at the back, but I appreciate this chuckle on the right-hand side. It's worth it. Who'd have guessed it? Okay, triple copying using variadic parameters, unacceptably cumbersome. All right, not a good thing to do. Those of you who chose option C, congratulations. Your borderline but not completely fatalistic pessimism is correct. Pure type-driven design is incompatible with sensible Go programs. Okay? Sensible type-driven design is compatible with sensible Go programs. So all that's left to do is find the point of maximal utility. Where is this most useful to you as an actual reasonable software developer in your day-to-day work? Okay? Do pass your raw inputs into valid domain objects and use exported constructors so that these objects, when they're out beyond the confines of domain, can only move from one valid state to another. Okay? Do use those getters and setters. And I actually recommend you consider using build tagged assertions to sanity check all manner of things that you assume can never happen, because I absolutely guarantee some of those assumptions are wrong. Never events happen all the time. And you can catch a lot of these at dev time with no production impact whatsoever. Okay? And I also suggest that you consider using an option of T to represent optional values much more expressive than nillable pointers, to show you very briefly like what that looks like in practice. Rather than having a load of pointers to strings where the question arises, right? Is this a pointer to a string because this thing is optional, or because the person I'm working with just isn't that comfortable with pointers? Okay? This is far more expressive. Like, you can read exactly what this does. Just by reading the type, we've got email. Okay, the email is clearly optional. Password hash, optional, bio optional. Oh, the ID, absolutely required. Finally, I mean, don't treat your colleagues, your future self, your past self as dangerous psychopaths. Do use pointers, right? It'll save a lot of copying. Your programs will probably run better. Profile to check, but just don't rule them out. And trust your team not to mess it up. And then they will mess it up anyway, but that's fine. It's software development. It's a team sport. We will fix it together. And just don't, please, and I really do beg you, I stress this point, never decompose your maps into variadic pairs in the name of purism. And my name, again, is Angus Morrison. Thank you so much. Those of you who couldn't see the codes, it will be available. I will share that link. Thank you.